Okay, so when we're trying to control an AI, there are basically two ways to go about it. We can either talk to it, give it examples, or we can do something that's more like digital brain surgery and just tweak its insides directly. Now, on the surface, those two things sound completely different, right? But what if they're actually two sides of the same coin? That's the incredible puzzle we're digging into today, a brand new theory that connects these two worlds.
So on one hand, you've got in-context learning. This is what most of us are doing all the time. You guide the AI with prompts, with examples. You're essentially teaching it what you want. But then you've got activation steering, which is, well, a much more direct approach. This is like popping the hood and manipulating the AI's neural network to force it to behave a certain way. One is teaching, the other is tweaking.
And that really is the central mystery here, isn't it? How on earth can showing an AI examples and literally manipulating its internal wiring be related? I mean, they feel like they come from totally different universes, and yet some fascinating new research is suggesting they're just two different ways of doing the exact same thing.
To really get to the bottom of this puzzle, we first need to get a bit more specific about how each of these control methods actually works. All right, so in-context learning, or ICL for short, it's all about what you put in the prompt. You give it examples, you give it instructions, you basically show the model what you want it to do. Activation steering, though, that's a totally different ballgame. It's an intervention. You go right into the model's internal network and you adjust what are called its hidden activations. You're not just showing it what you want, you are fundamentally changing it to be what you want. So how could these two totally different approaches possibly be connected? Well, the secret, the hidden link, lies in this idea of the AI's internal beliefs. Here's the core theory, and it's pretty wild. Both prompting and steering are just different ways to adjust the very same dial inside the AI. And you can think of this dial as the AI's belief in a certain concept, maybe a personality trait or a particular style of writing. Both methods are just trying to turn that one dial either up or down. Now, this process is modeled using a really powerful idea called Bayesian belief updating. And don't worry about the fancy name. You can just think of it as the mathematical rulebook for changing your mind. It's a formal, precise way to calculate exactly how much your beliefs should shift when you see new evidence. And this diagram just lays it out perfectly. Over on the left, you've got the two inputs, your prompts and your direct steering. But look at how they both funnel into that single crucial step in the middle, updating the AI's internal belief. It's only after that belief is changed that the AI spits out its final behavior. This is showing us a common engine hidden under two very different hoods. Okay, so if both methods are changing the same internal belief, how exactly do they pull it off? Well, it turns out they persuade the AI in two completely distinct ways. And this right here is the critical difference. In-context learning is like adding evidence to a scale. Each example you give it is like one more little weight, slowly but surely tipping the AI's belief one way or the other. Activation steering, though, is like putting your thumb on the scale from the very beginning. It changes the AI's priors, its initial bias, its starting point, before it even sees a single piece of evidence. So, think of it this way. In-context learning is a slow burn. It's a journey, where each example is a stepping stone that gradually builds up the AI's belief. Steering, on the other hand, is like putting the AI in a specific lane from the get-go. You're setting its default path, making it naturally lean one way or another before it even starts its journey. All right, so this is a really elegant theory, but does it actually hold up in the real world? To find out, researchers designed a pretty fascinating set of experiments to really put it to the test. What they did was they tried to push a large language model to adopt some pretty harmful personality traits. We're talking about stuff from the dark triad, Machiavellianism, narcissism, that sort of thing. The goal was to measure exactly how much control they could get over these personas using both prompting and steering. And the results were, frankly, incredible. If you look at the top graph, without any steering, that blue line, the AI follows this classic S-shaped learning curve. But watch what happens when they turn on steering. Positive steering shoves the entire curve to the left. That means the AI adopts the persona much, much faster, with way fewer examples. And negative steering? It pushes the whole curve to the right, making the AI way more resistant. It's clear proof that steering acts like a powerful multiplier on the prompts. Because this interaction turned out to be so consistent, it allowed the researchers to do something really remarkable. They were able to create a predictive map of the AI's internal state, what you could almost call a map of its mind. And here it is. This is the stunning proof. On the left, you're seeing a heat map of what the Llama 3 model actually did under all these different conditions. On the right, you see what the Bayesian belief model predicted it would do. I mean, just look at them. The patterns are nearly identical. This means the theory isn't just some nice explanation, it's a working, predictive model of how this AI thinks. Now, having this kind of predictive power is way more than just a cool academic finding. It has huge implications for one of the biggest challenges in AI today: safety. Because this model is so incredibly accurate, it can do something amazing. It can predict the phase boundary. That's the precise tipping point where an AI's behavior can suddenly and dramatically flip from being safe to being harmful. And just how accurate is it? Get this, the correlation between the model's prediction of this tipping point and the AI's actual tipping point was 0.97. That is almost a perfect prediction. It's ridiculously accurate.
And this has direct, real-world applications. The researchers themselves point out that this gives us a concrete way to predict many-shot jailbreaking. That's the critical safety flaw where an AI's safeguards can suddenly just collapse after you nudge it with too many seemingly innocent prompts.
So this all leaves us with a pretty profound final thought. We now know that teaching an AI and tweaking an AI are really just two sides of the same coin. They're both just different ways of updating its internal beliefs. And this understanding gives us a powerful new tool. So if we can now predict an AI's breaking point with this level of accuracy, the next great challenge seems pretty clear, doesn't it? Can we finally learn how to prevent it?